Right. So our second speaker today is former Director of Variable Stars South, Stan Walker. And as most of you probably know, Stan's contribution to variable star research in the Southern Hemisphere is exceptional. It's going back many decades to the very beginnings of photoelectric photometry, and right through to today, he's still producing papers that are pivotal in some ways. So today, Stan will be talking about dual period Cepheid variables, I believe. Yes. His second talk in 2 weeks' time will be on dual maxima Mira variables. So two topics that he was very much involved with early on, and in an observational sense, I believe. But nowadays he's doing a lot of analysis of historical data, and so I'm looking forward to seeing what Stan has to say today. So over to you, Stan.
And Stan, just let me know when you want the slides advanced.
Many thanks there, Mark. Might be heard?
Yes.
Okay. Mark's covered some of the aspects of things. Once ago, up until a decade or so ago, I used to observe, but these days, old age is catching up with me. So, and the stairs up to the dome are too steep. So I've been analysing a lot of visual results. They're quite interesting. And what began as a simple project that it tells me a lot about how good and how bad visual observing can be. And it's pretty much a work in progress. The concept of 2 periods is valid, but help is necessary to really prove it and sort of tie it up. We've got to drop some old ideas and bring some new ones in. The time scale is pretty long, but all visual observing is like that, and give some thought to the past observers whose data are being used. The earliest I've used in what I'm doing was Cepheid measures in 1864, when the first one of the first photographic catalogues became available. A lot in the 1890s and 1910, 20. So what I'm really talking about is visual measures today. And they're very good if they're planned correctly. I think they're more interesting to beginners than Miras. Certainly they vary in brightness a lot faster and they change periods a lot more. The thing we've got to realise, though, is it's the quality of measures, not the numbers, which are most important. I'm very much against the concept of awarding prizes for how many stars you observe. It's the quality that matters. And I think that most visual observers should select a small number of stars, look at them and regularly, understand a bit about past observations of them and the results they're getting now. But like all amateur research, it needs much more discussion and sharing. I'll have the next. Right. The abstract, I think this was published, so most of you should have read this, and I've virtually covered this in the comments I've made there. So let's look at one of the light curves, or one of these stars. It's a very bright Cepheid, one of the brightest, and it's been observed since the 1890s, I think. And you can see that if we plot the calculated ephemeris against the actual measures of maximum brightness, that for a long time it had a period of 38.76 days, but about 1983, it then changed and became a bit longer. But the interesting thing here are the oscillations in the light curves itself. And this is what I have been looking at. Next one. Variable Star South has got a lot of its members to make measures of Cepheids, visually or photoelectrically. And by we collected a lot of them up, and we've now reached a stage where a number of these are showing some interesting things. We're mainly interested, or the ones that show the changes are cooler Cepheids, which are much, well, let's say the brighter Cepheids tend to be a little bit overall cooler and a little bit redder, and they have convective envelopes all or part of the time. So we are thinking that the alternative periods probably comprise the accepted pulsation down in the radiative region, which is very, very regular. And the fact that this shows some variations, slight variations, can't be explained by this fundamental method of pulsating. So what we think might happen is that there are periodic changes in the convective envelope, which the radiation must travel through in order to reach the surface and be then radiated again. And the combination of the two is why the Cepheids themselves vary. Next one. Okay, this is a brief look at the idea of what we think the sun is like. And the important thing here is the change from a radiative region here in the inner part of the star to a convective layer on the outside. And the steady pulsations, much longer in period, occurred in this as a result of disturbances in this region, and then they are modulated by as they travel through the convective envelope. Another one. If we look at the HR diagram, we see that we're a whole region devoted to Cepheid type pulsations. I think where they reach down to the main sequence with some very short period stars. But the classical Cepheids, the ones we tend to be looking at, are in this region from periods from about 3 to 45 days. Longer periods in 45 days seem to be pretty unsteady. And I doubt very much that there's really the Cepheid mechanism we're looking at then. The stars are brightest at minimum size and faintest at maximum size. At minimum size, they're hottest. At maximum size, they are coolest. Now, in 1995, I got the date wrong there, but in 1995, we presented a paper at the IOU General Assembly pointing out that we're pointing out all the stuff we just talked about. Next one. And with Mira stars, it tends to produce an O-C curve of this nature. We're plotting a fundamental period here of 334.1 days, but you can see that it varies backwards and forwards in a sort of a sawtooth pattern. And this, we think, is the superimposing of the variations attributable to passage of radiation through the, or energy through the outer convective layer. Now, there's every Mira seems to show this, also some of the semi-regular stars with periods in the Mira range. Next one. You with me, David? Another one?
Yeah, sorry, I just had a slight hiccup there.
Okay, let's return and look at Eucharini in more detail, or Carina, I'm never too sure how to pronounce it. We show seasonal epochs. Oddly enough, Cepheids are measured only in seasons. They tend to occur in the plane of the Milky Way, which passes across the southern hemisphere, more or less from autumn to late spring. So we have a 6 to 8 month observing period. We take about anywhere between 20 and 40 visual measures, mean them, and determine an average epoch of maximum for that season. As I said before, there was a major period change in 1983, but it's the small wiggles which we're mainly interested in, which the next slide shows. One more, David. And after extracting the fundamental period from it, we get a plot of the secondary period. This covers, as you can see, 14,000 years and goes, 14,000 days, and goes through 2 cycles. So each cycle is about 20 years long. These measures were mainly made by Peter Williams, who's the blue points, but later on, one of our other members, Alistair, was Andrew Pearce, shown by the red squares, and AAX, who I think is a South American observer. I don't know him at all. But it's similar to a Mira-like curve, but the amplitude is less, although it's a percentage, it's probably about double the Mira amplitude. On to the next one. And that also was seen, okay, by some of the early observers. One of the most prolific early observers was a gentleman called Alexander Roberts, observing in South Africa. It's interesting that, he observed through the Boer War and the Great War. And once again, you can see, although not to the same extent, once again, a periodic variation with roughly the same period. Next one. So we've been, I've been trying to encourage a lot of visual observers to look at these, and some of them have listened and made measures. This is what we're working on. The photoelectric observers tend to get very enthusiastic, produce a light curve. Then once they've got a light curve, the job is done and they move on to something else. Basically, we're interested in a much longer scale of study. So we're using visual observations, which have their limitations. A good sequence and good comparisons will probably allow a experienced visual observers to reach 1 or 2.01 or 0.02 accuracy. The Cepheids themselves, some of them have amplitudes up to 1.5 magnitudes, and a usable number are between 1 and 1.5 magnitudes. We get them out of the international database maintained by the AAVSO, but most of the observations we use will be from the RASNZ and also the BAA, both doing a lot of observing in the Southern Hemisphere. And like most pulsating variables, epoch maximum brightness occurs earlier at shorter wavelengths. So if you measure it through the B filter, you will see the maximum brightness earlier than in V. And with a period of about 40 days, the difference is about 2 days, which is quite a large amount. And okay, it makes, because visual observations are more or less all at the same wavelength, it makes the whole study a bit easier. The cycle length is quite long, several decades, but there have been people who have looked at the same stars for 20, 30, and 40 years, which shows dedication, they're good, and their data is quite reliable. Next one. There's our target list. The interesting part is the rise time. The longer the period, the more quickly the star will travel from minimum brightness to maximum brightness. Some interesting thoughts in that one, but it certainly makes it easier to observe the longer period ones because their rise time is very sharp and very short. Next one. And this is one observer's measurements. We blotted out his name up here, fitted to that blue line, which is the mean light curve of this particular star. Which one is it? Yeah, that's once again Eucarina. This allows us to change 3 factors, which will become the reason for this become quite apparent. We can offset the magnitude if somebody is using the wrong sequence, which is fainter than another sequence, the measure will be displaced up or down. The amplitude factor, once again, because of the faulty sequences or the different sequences, sometimes somebody will have the star varying through 1.2 magnitudes, other times through 1.5. So once again, we can correct for that. And then the time offset shows us how much the epoch of maximum differs from the calculated epoch of maximum and allows us to construct these O-C diagrams I've been showing. On to the next slide. So we have to, on to the next one. I've explained all that. Now, unfortunately, are you seeing the whole picture or just, are you getting the whole picture there, David?
I can see the whole slide. There's 2 graphs.
So not the right-hand side isn't blotted out. Okay,
No.
Good. Now, if you take the top half, it looks really messy. And you wonder how we can get a reliable epoch of magnitude out of that, or epoch of brightest magnitude, seasonal. But because we can vary those 3 factors up and down, we can then slide them up so they overlap and expand or contract them and so forth and so on. Now, all this was, the device which does all this was constructed by Mark Blackford using Excel, and I use it a tremendous amount in order to get this information. We perhaps don't use the automatic version of his as much as possible because we get a few, tend to get a lot of scattering in the visual wavelengths. So we rely much more on measuring the time of occurrence of this rise to maximum. Next slide. Next. How do we avoid these problems? Well, very simple. Different observers use different comparison sequences. And sometimes the makers of the charts put so many stars on there, a lot of them with poor magnitudes, that nobody is using the same stars to measure the brightness of the variable. Now, when we started photoelectric photometry, the thing that you did, or was essential, was that you made your measures using exactly the same comparison stars that other people had used. And even if they were wrong, at least all your data was compatible. The Cepheids are good because we only need about 5 or 6 comparison stars covering about 1.5 magnitudes. I don't like the idea of publicizing the number of measures that observers have made. I think that leads to not enough time being spent upon quality and too much upon quantity. And if they're in a hurry, the guys with binoculars tend to make say that the brightness is equivalent to one of the comparison stars. It's easy to get a measure that way. Onward. Okay, second, another star, RS Puppis. At the top, we show the O minus C, or the observed minus calculated epochs of maximum as against the periods in the GVS. We then worked out our own periods and corrected partially for them. But the next slide shows a different approach to it. And here we see along the top all of the observations corrected for to the period which was in force at the time that the measures were made. Oh, sorry, that's a lot. Then along the bottom, this curved thing shows what a standard O minus C light curve or observed minus or deviations would show. You can see that here the period was too long, and it was too short. There was near enough, about right, and now here the period is calculated period is too long. RS Puppis also shows these small amplitude variations. I didn't have time to correct the graph. The next one. And even back with Roberts back in the 1900s, you can see once again they're there. So these things obviously are not random walks. They are variations occurring somewhere. And we believe that they're occurring in the convective envelope. Next one. Just a few stars, Aries Scorpii. The convective envelope ought to be much thinner, with periods of about 20 days. So we're not seeing very much of the secondary pulsation or variation. On the other hand, if we go up to a 45-day star, SV Vulpecula, you can see once again the variations are there. Perhaps the period was increasing, but it was a bit hard to tell. Keep going. Oh, sorry, Tumanoceros. Now, once again, here's a star where we just have too much data. We've tried to pinpoint some of the observers, and you can see that the curves are all over the place. And this, unfortunately, doesn't sort of lend itself to the treatment which we managed with U. Carini. Next one. So, okay, that's what I really wanted to talk about, but two final slides. The thing after looking at all of these things and analysing, I concluded that it's probably better to get beginners in astronomy to concentrate for a season or two on looking at Cepheids, perhaps longer if they want to, because Cepheids are more active. Because they're more massive stars, they evolve much more quickly. A long time ago, many decades ago, main sequence stars were supposed to evolve at something like 3 3/4, or the mass raised to 3 3/4 times. So they go faster. In all of the Cepheids I've looked at, none of them show a steady period. They all have at least one variation a century. In the case of RS Pupus, 3 or 4 variations in a century, which is encouraging that stars doing something. RS Pupus is also doing something else because it's surrounded by a dust and gas nebula velocity. The comparison sequences are more reliable. They don't have to be so big. Ideal for small telescopes and binoculars. And because they're doing things, it's good to get light curves much more quickly. You can plot them on Excel and you get feedback and enjoy it. And the last one, I think. Okay, what do we need for accuracy? The observer can't control any of these. Perhaps I need to persuade somebody in VSS to make our own Cepheid charts, but they want a suitable comparison sequence with no duplicates. Now, comparison sequence quite obviously means that you have one star for each step in the brightness or faintness, not a dozen or 100 as in some of the VSO charts. The season is relatively short. You've got time to do something else for a while. If they concentrate on the rising branch, certainly eating the long period stars, they need to make fewer measures and they will get a better answer. On the other hand, you do need to make 1 or 2 at maximum or minimum, just to make sure that the star has got the same scale that you think it has. Avoid some sources of error. Don't assign values identical comparison stars. There's some 2 or 3 guys, 40% or 60% of their measures equivalent to one of the 2 or 3 comparison stars in the field. Obviously, quality is required, not quantity. And looking at objectively, a single good measure of 40-day Cepheid is worth 10 of a 400-day Mira. Plot your results in Excel. If you get tired of looking at the bright ones, get your telescope out, even if you haven't got all these fancy filters and CCD cameras and whatever, you can still make visual observations through your telescope. But always send the results to the international database. Yeah, that might be the last slide. It was. Many thanks.
Thank you, Stan. That was very good. It seems like there's a lot of work to still be done, though.
Oh, yes.
Yeah. Is there a place for CCD measures in this study, do you think, or do we need to rely on the visual people?
No, quite obviously, CCD or DSLR measures are more accurate. The Cepheids do have a quite a changing colour, so they're not. DSLR is still good, but not quite as good as CCD. But what is really needed is just to take a Cepheid and don't try and get the full light curve of a Cepheid. With a CCD, you only need 10 measures if they're well distributed. If you have one up maximum, one up minimum, you can get away with 3 on the rising light curve. So the best thing to do there is pick a dozen or 20 stars and concentrate on measuring those for 10, 20 or 30 years. Or you put in your 5 years, then get the next guy to take over. That is much more effective. You don't need vast numbers, but you need.
Right. Maybe we can talk offline about how we can aid that. But yeah, that's very, very encouraging.
Sorry.
Any other questions?
Yes.
Okay, Greg.
I'm wondering whether a common theme in both Edwin's presentation and in Stan's is that folding light curves over one another, theoretically to use statistics to home in on the actual curve, you are in fact obscuring the minor variations, which would have more to tell us. Is that a correct understanding?
Yes. Basically, I would say yes.
Well, our feeling about Cepheids and Mira to that extent is that the main light variations are caused by what do you call losing an electron from the nucleus and then recombining, ionization and recombination. Now that seems to explain the fundamental period quite well. Once you get out into the convective area, well, quite frankly, I have no idea what these low amplitude variations are. Brian Warner, who a specialist in cataclysmic variables, said, well, you're probably dealing with a change in the number of massive cells in the envelope. But you are dealing with a convective envelope, and there will be lots of minor variations, as our man says. But okay, we know the overall long period. I'm now working on a secondary period, which is about 2 to 3% of the main period. But undoubtedly, on top of that, there are all sorts of things. Just look at the sun. I mean, that's a good example of a star with a convective outer layer. And it does all sorts of things, doesn't it?
Indeed.
And at the present moment, we haven't, well, with the sun, we can measure them and understand them. But that would be an extremely massive task doing it for, say, even all the Cepheids, if you limit them to 50.
Yes. Yeah.
It doesn't help your query. The answer to your query basically is it's a good thing, but it takes much more ability than we have. And since I am trying to suggest something suitable for visual observers, it's just way out of their range.